Hi, let us proceed with our discussions with the testing of a beam in the heavy structure lab. Previously, we mentioned about monitoring the load displacement response of the specimen during testing. We also talked about the load control mode and the displacement control mode. To ensure a smooth plot throughout the load displacement curve, you may need to combine the load control modes and the displacement control mode. This is especially when the specimen has yielded, the displacement of the member increased significantly. If you are still in the load control mode, there will be less plot for the load displacement curve, and the curve becomes not as smooth as compared to those with more plots. If you look at the procedures of conducting the testing, we are also monitoring the propagations of the crack throughout the test. You apply the vertical load onto the specimen, and then you hold the load for 1 minute before readings are taken. Then you look at the surface of the beam, see if there is any crack occur. If you observe any cracks on the surface of the beam, you can use a marker to mark the locations where the crack ends. Indicate the load level when the crack ends. Once everything is done, you increase the vertical load further, and you observe the further propagations of the crack. Normally, the first crack will happen at the midspan. As the load increases further, more crack will occur. The crack propagates deeper and deeper into the beam as the vertical loads increase. After the first crack, there may be additional crack at an offset distance from the first crack, closer towards the support. The same goes to the other side. Hold the load for 1 minute, take the reading, trace the crack, and mark the locations where the crack ends. You need to check every single crack if there is any further propagations. Let's say now we are at 88 kN load. This 3 crack does not propagate further, while this crack ends here. Indicate the load level, and then you proceed with the next load level. You will repeat the process to observe the propagations of the crack further. Now, if you combine the photos together, you will see the propagations of the crack until the failure of the specimen. Personally, I do not recommend you to trace the crack line, as the crack width sometimes also gives you significant information. It reflects the severity of the crack, indicating the failure modes. Let's say now if you embed something in the beam specimen, the rate of propagations of the crack may bring you some additional informations regarding the response of the specimen. For example, if you have void somewhere here, it is expectable that the crack will propagate faster at this region. Back to the point just now, normally I do not recommend you to trace the crack line because you can observe the crack width to give you some idea the critical damage of the specimen. If you look on the surface of the beam here, this crack line here seems to be more critical than the crack lines here. The crack width is wider as compared to the others. However, for the sake of presentations, sometimes researchers in their publications trace the crack lines. This is to demonstrate the crack lines and the crack patterns, so that there is sufficient contrast to indicate to the reader regarding the crack patterns. You know that based on the crack patterns here, different types of the crack can be observed. We have flexural crack. This kind of crack normally happens at the midspan of the specimen, when the specimen is subjected to the pointlets. We have 2 pointlets here and 2 reactions here. Based on the bending moment diagram, we will expect high moments at the midspan. And based on the shear force diagram, the shear force is relatively low at the midspan. That means this is the regions where the flexural load is dominant. The flexural crack normally start from the soffit of the beam at the midspan. It is normally the first crack of the beam when subjected to the 4 pointlets. Starting from the soffit, and it goes upward. The larger the vertical load, the deeper it goes, the larger the crack width, and additional flexural crack occur at an offset distance from the previous crack. In terms of the characteristic, it is generally vertical crack. You see random movement of the crack fluctuating along its pathway. Even so, ultimately there is a direction. That means this kind of crack is a live crack. The random movement here is due to the aggregate, which is random embedding in the beam. The crack will develop at the weakest locations by passing the aggregate, either due to the tensile failure of the concrete or bond failure between the cement paste and aggregate. We have another type of crack which is known as the flexural shear crack. This kind of crack is combinations of the flexural crack and the shear crack. It normally occurs at a certain distance from the support, somewhere between 1.5D to 2D distance from the support. The D here represents the effective depth of the specimen, which is the distance between the top surface of the beam to the center of the tensile reinforcement. Normally, flexural shear crack will not happen at the midspan. Now, it depends on the locations of this vertical load. If the distance of the vertical load is far away from the support, the flexural crack will be dominant. You will see a lot of crack will go vertical. Now, if this point load here is located very close to the support, shear crack is likely. And the flexural shear crack, it will be somewhere intermediate between those flexural crack and the shear crack. This is often seen in the specimen with the distance between the point load to the support here less than 6 times the D but more than 1.5D. Now, how do you identify the flexural shear crack? You can identify by the locations, normally somewhere between 1.5D to 2D. Another way is by looking at the pathway. Normally, the flexural shear crack start vertically. Deeper into the beam, it will become diagonal, and it is heading towards the point load. There is a reason why it is so. You can imagine in this manner. You have a beam here. When subjected to the load here, the beam tends to deflect. Now the soffit of the beam undergoing tension, while the top part of the beam will undergo compression. The flexural tensile stress will be the highest at the soffit of the midspan. It reduces further away from the center. If you plot the contour of the tensile stress, it should look something like this. High stress at the middle and lower stress further away. That's why the first crack normally happens here. The crack happens when the concrete has exceeded its maximum strength. When the stress increases further, a wider region of the concrete has the strength exceeded the capacity of the concrete. Then you will have additional cracks further away from the center. If the crack develops at the midspan, you will expect the cracks will go vertically upward. Further away from the center, the crack will become slightly diagonal due to this tensile stress contour. Closer to the support, when the tensile stress exceeded the concrete limit, it starts with the flexural crack. As it goes outward, the crack will go along with the regions of larger tensile stress. Let's say the imaginary contour, it will be something like this. When the crack reaches here, it shall go in this direction, as these regions will have relatively low stress as compared to this region. That's why deeper into the specimen, there will be inclined crack. The third type of the crack, it will be the shear crack. This kind of crack normally happens near to the support. It is typically an inclined crack, and normally it happens rather fast. The beam with flexural crack more dominant will have a more ductile failure. Meanwhile, the beam that fails with the shear crack normally fails suddenly. This shear crack here doesn't necessarily always start from the soffit. Sometimes it can start somewhere here due to the diagonal tensions of the member. This is about different types of the cracks. Now, based on the crack pattern here, we are able to identify the failure modes of the specimen. Now, the failure modes here is defined based on the severity of the crack. What does it mean by the severity of the crack? We look at the crack length, we look at the crack width, and also we look at the highest load achieved by the respective crack. Crack length is easy to understand. The longer the crack, it seems to be more severe. Crack width is also easy to understand. The wider the crack here, it seems to be more critical. How about the highest load achieved by the cracks? We look at the last number as given at the end of each crack. The number here represents the load level where the crack ends. Which crack line gives you the highest value of the load level? It is likely that the critical failure is due to the crack. Nevertheless, you will still need to observe the typical crack pattern and make reasonable judgment. You can observe from various aspects, not only these three in terms of the severity of the crack. You may observe the ductility response of the load displacement curve. If the critical failure is due to the shear, brittle failure is likely. Normally, you will observe a significant drop after the ultimate load. If it is due to the flexural failure, it is more ductile. The drop is not as significant. Now, in terms of the failure mode, there are three types: flexural failure, diagonal tension, and shear compression failure. Flexural failure will have the flexural crack more dominant. The flexural shear crack may or may not be present. Normally, there is no shear crack, or the shear crack is relatively minor. These are the criteria to determine a flexural crack, where the width of the flexural crack is the largest as compared to the others. the length of the fractural crack is the longest, or the recorded load for the fractural crack is the highest. The second type of the failure modes is known as the diagonal tension. This normally happens when the fractural shear cracks were dominant. From the perspective of the test setup, the distance between the point load and the reaction force here normally will be somewhere between 1.5D to 60. More than 60, fractural failure is more likely. If the distance here is less than 1.5D, shear failure is more likely. For you to determine the diagonal tension, you may look into these criteria, where the crack width of the fractural shear crack was the highest, or the fractural shear crack is the longest, or the recorded load for the fractural shear crack is the highest. Similar concept goes to the shear compression failure. That means the failure is more dominant due to the shear crack. Now for the diagonal tension here, the shear crack may or may not be present, and normally fractural crack should have already been developed before the fractural shear crack. In another word, there will be fractural crack, and the fractural shear crack will be more dominant. As for the shear crack, it may or may not be present. Now when come to the shear compression failure, the shear crack is dominant. Now this shear crack here may or may not reach to the top reinforcement of the beam, and the top beam may or may not be crushed due to the load. Depending on the test setup, the specimen that failed due to the shear may not necessarily have the fractural crack or the fractural shear crack. It is possible to have shear crack alone. We also look at the crack width, crack length, and the recorded load to determine the shear compression. Please note that the method to classify the failure modes may differ slightly among researchers. This is an example for us to objectively determine the types of the failure, for us to analyze the behavior of a beam more systematically. You may have your own ways to determine the modes of the failure. The ultimate goal here is to identify the critical damage of the specimen, so that you know the weakness of the specimen and how can you improve the specimen further.